Okay, so we finally got all the technical problems figured out, I think. Um, and we will be talking about all of the highlights that you should have gotten from week one. Hopefully, if you're still struggling with any of the topics, they will make a little bit more sense. This is the processing type of work that you have to do. So what we start with is knowledge that you already know, hopefully. You should know the Pythagorean theorem, and we're used to that being a squared plus b squared equals c squared, or leg squared plus the other leg squared equals the hypotenuse squared. So we can think of it that way. We did this with our 45-degree triangles, 45, 45, 90, which we know the two sides are equal. We can call that n and n. We're eventually going to be talking about circles and putting things on the coordinate grid. All circles are similar. All 45, 45, 90 triangles are going to be similar, meaning the sides are going to be in proportion. So if we're looking for the generic ratio for things, we can pick easy numbers to work with. And in the most case, we're going to pick the radius being 1 or the hypotenuse being 1 as our number, just because in the future we're going to have circles with radiuses 1 and stuff like that. So a little bit of manipulation, but all of the things being in proportion means that we can do this. And then our Pythagorean theorem becomes n squared plus n squared equals 1 squared, which we did in another video. So this is 2n squared equals 1, n squared equals 1/2. You can square root both sides to get n by itself. Remember, when you square root, it could be positive or negative, but because we're talking of a distance, this is a length, it's going to have to be positive because we don't have wormhole theory working really well yet. So this is going to be n equals, and if I'm square rooting a fraction, I can square root the top and square root the bottom. So this is going to be the square root of 1 is 1 over the square root of 2. Now we have this thing of rationalizing the denominator, meaning we don't like square roots to be in the bottom of a fraction. It is not as end all be all as it used to be with technology that we have. However, it's still a good practice. And when you go into calculus, you're going to sometimes have to rationalize the numerator so that you can do other functions. So rationalizing is still a good skill to know. And to do that, we multiply the top and bottom by the square root in the bottom. We can do that because we're multiplying it by a factor of 1, and 1 times anything is that nice number of whatever you had that you were multiplying. So this is going to become n equals 1 times the square root of 2 is going to be the square root of 2. Square root of 2 times square root of 2 is just going to be 2. And that's how we get those sides for that 45, 45, 90 being square root of 2 over 2, square root of 2 over 2, and 1. That's not a 2. That's okay. And then we also looked at the 30, 60, 90 triangles. If I'm looking at this triangle, notice all my triangles are kind of in the same position, which is going to make it a little bit easier to refer back to for when we go on the quadrant grid. I usually have things in standard position. We're going to talk about that specifically with angles, but that just means my vertex is going to be at the origin, and then I'm going to be going along the positive x-axis for one of them. So most of my triangles will look very similar in the same notation of what we're going to doing. And this triangle, if I'm looking at it, it is the bigger leg is going up and down. So this has to be a bigger angle because the sides go in proportion to the angle size that they have. Smallest angle is going to be across from the smallest side. So this one is going to be a 60 degree. And I know with the 30, 60, 90, because if this is 60, this has to be 30, and this has to be 90, because they all add up to 180 degrees in any triangle that you have. And I always know, so this is going to be a 30 because my short side is shorter going up. I know in any 30, 60, 90 right triangle, the short side is always going to be half of the hypotenuse, or the hypotenuse is twice the short side. Yet again, I'm going to make my hypotenuse be 1 because I can control it. And then I'm going to say that this is my short side, so it's going to have to be the 1/2. If I was working in this triangle, my hypotenuse may be 1, and this time my y value would be the 1/2. All right, so I have a little bit more room above the 30-degree triangle, so I'm going to label this n because it's what I'm looking for. And actually, instead of n, I know it's in the x direction, so I'm going to, in this case, call it x. Okay, so this is x, and then my Pythagorean theorem is still going to work the same way. I have the x squared plus the side I know, which is the 1/2 squared, equals, yet again, 1 squared, which is the hypotenuse. When I'm squaring a fraction, I square the top and square the bottom. So I have x squared plus 1/4 equals 1. If I want to make it easier, because I struggle with fractions, I can make this into a fraction as well, because fractions always work best with other fractions, so I could call this 1/1 if I wanted to, or I'm just going to leave it as 1 to be perfectly honest. All right, so to get x by itself, I'm going to get x squared equals, I'm going to subtract that 1/4 from both sides. 1 minus 1/4 leaves me with 3/4 left. So if I do make it a fraction, I need to make it, instead of a 1/1, I could start with that. But then I need it to be the same number of pieces, because the denominator is the same number of pieces. So 1/1 is the same thing as 4/4, and then 4/4 minus 1/4 is 3/4. Now I'm going to square root yet again, keeping in mind that it's always going to be positive because I'm talking a distance, because we're talking sides of a triangle. The x and y values can be negative because when we start looking at the coordinate plane, the quadrants can be negative, so we can go in a negative direction. We just can't go a negative distance. So all of our radiuses are always going to be 1 because they're always going to be a distance regardless of where we're looking at. And then I'm going to square root the top and square root the bottom. So square root of 3. And the square root of 4 is 2. So this side is the square root of 3/2. And if I was in this triangle, the 60-degree triangle, this would also be the square root of 3/2 because they're always going to be in those same proportions. So these are the numbers that you're going to want to be thinking about. In a 30, 60, 90s, I have the sides 1, 1/2, and square root of 3/2. In a 45, 45, 90 triangle, I'm going to have the two sides being the same. And if I've got a radius of 1, it's going to be 1 square root of 2/2 and square root of 2/2. Pythagorean theorem, you can always keep working with it. Base factor, we use the Pythagorean theorem a lot, even though we don't tell you that you have to do the Pythagorean theorem to solve a problem. It's underlying understood. So we can also change it to the x squared plus y squared equals r squared, which is what we're going to be using a lot because we are going to be on the x and y axes. All right, so we got the special right triangles. Pythagorean triples, those are the common right triangles where the sides are nice numbers, always works in the Pythagorean theorem, and we don't have decimals. So you're probably familiar with the 3, 4, 5. Okay, and I could double the sides, so it could be the same as 6, 8, 10. I recommend looking up your Pythagorean triples and knowing at least the first 3, possibly more, of what they are, what the ratios are. So like 5, 12, 13 is going to be one of them. Yet again, Google, great thing. Look up your Pythagorean triples. It'll just save you some time. You can always use the Pythagorean theorem. If you happen to know that something is a triple, sometimes makes your life easier, but sometimes also can make it a little bit worse if you're expecting it to be a Pythagorean triple and the number that's usually the hypotenuse isn't the hypotenuse. Then it can cause you problems. So always be careful. Which is why memorization is not always the best thing. Understanding is way more important. So we're going to draw an XY axis. And I'm actually going to use the line tool because I cannot draw straight lines. You will see very quickly when we're trying to draw angles in here. All right, so we have an XY axis. I think I'm going to change colors because I can. All right, so this is the X, this is the Y. This would be our negative X, negative Y. If I'm talking a circle or in measuring angles, I usually, if you notice, I go draw my triangle. I'm going don't draw anything. I'm just using my pointer and I'm going counterclockwise. If we remember that this is quadrant 1, because everything's positive, we start by learning our numbers on a straight line in a number line. So that's really makes sense for our 1. And then we go to quadrant 2, and as we're doing this, we finish completing the x squares. Y's are positives. So we're going counterclockwise for our quadrants. This is quadrant 3, and this is quadrant 4. We have the x the X and Y axis intersect here. So this is the origin at 0, 0. When we're going to be talking about degrees, radians, and stuff, they can be the same angle. We're just kind of looking at it from two different perspectives. Same type of thing. Circles, we can think of the inside turn, so like a spinner, in which case we would start here, and this would be 0 degrees. And if we went all the way around, we would get a full circle is 360 degrees. If we go halfway around, we have 180 degrees. And then if we go half of half, that would be 90 degrees. And then halfway between 180 and 360 is 270 degrees. Now, we don't have to think of it as the inside part of a circle. We can also think of a circle as the outside edge. And we know that the outside edge is the circumference. I shouldn't put it here. I'm realizing it is by different terminology, and that might make it look terrible. All right, so we're going to put it over here. Circumference. And that's the distance around. It's like the perimeter of a circle. And we should know that circumference equals pi times diameter. Diameter is 2 times radius, so it's also pi times 2r. We usually put the 2 in front, but we're going to leave that as pi times 2r. What we're going to be talking about, because the easiest number to work with is ones. So we're going to have a radius of 1 and a radius of 1 and a radius of 1 all the way around. So in that case, the circumference is going to be, the radius is 1, the diameter is 2. So the circumference would be 2 pi. That is talking the same angle that we were dealing with when we were doing the turning. So if we're talking outside edge, the circumference is also going to be related to our radians, because a radian is the distance or the turning to cover an arc length, so an edge of a circle that is 1 radian long. So we have, this is going to be still 0. It's 0 radians. I haven't moved. If I go all the way around the circle with a radius of 1, so this point would be 1, 0, then my circumference is just 2 pi. So whole way around the circle, 2 pi. Didn't need to write that twice, but I did. Now, if I only go halfway around, I have gone half of a circle, and the whole circle being 2 pi, this would be pi radians. All right, and then hopefully we can work on our comfort with fractions. Honestly and truly, fractions make a lot more sense. They're a lot less work. They're a lot easier. However, you have to understand the basics of it, and I think people start getting taught it a little too early before it really makes sense. They decide they hate it, and then they refuse to make sense of it. So if you can work on fractions, that's one of the skills we're going to work on. Yet again, we're not going to use calculators if we can avoid them. All right, so fractions are always the number of pieces you have or how far you've gone over the number of total pieces. So if I break this 1/2 of the circle, which is just pi, so if I do the pi into 2 parts, I would end up here. So this is going to be pi divided by 2. So this is 1 pi over 2. This would be 2 pi over 2 because I've gone 2 sections, which reduces to just pi. And then if I go down here, I've gone 3 pi over 2 because I've gone 3 of those halves. And then back here, it's 4 pi over 2, which is just 2 pi. Okay, so thinking about that, we're going to say, oh, what happens if I break it into 4 sections? Okay, yet again, my straight lines are actually not too bad today. I just spoke too soon. All right, definitely spoke too soon on that one. That is way bad. That has to get erased. Not even close. All right. That should be right here. Still not good, but so now this time we have 4 sections. If I was thinking about this, this is 180 divided by 4, which is 45-degree angles. So I'm thinking here, this is 45. But if I'm talking the outside edge, this pi, this half of the circle, is divided into 1, 2, 3, 4 sections. So this is pi over 4. This would be 2 pi over 4. So 2 pi over 4, which is just pi over 2, because I can divide both of those by 2. This will be 3 pi over 4 over 4, 4 pi over 4, which they cancel out, and I just have pi again. 5 pi over 4, and 6 pi over 4, which becomes 3 pi over 2. So 6, 7 pi over 4, 8 pi over 4, which reduces down to 2 pi. So that's how we can actually think of how we're breaking down that unit circle, thinking we're going to get to the unit circle. Notice I didn't draw a circle. My unit circles are just usually the axes because it's less to draw, less to think, but it gets me that concepts that I need to do. So think about where you are and how much you've broken the circle into. Trust me, it's going to take a bit to make sense of it. It also would take a bit to memorize the unit circle, and the unit circle memorization is pretty useless because then you have to draw the whole circle every single time you need to use it, and that takes longer. So it's going to take time to think about this no matter what. So let's do it the right way of understanding it. So this, if I was talking on my unit circle where I'm going through, so this was 0, 1, I have a radius of 1, which is like my triangle here. So that means that the point that is out here with a radius of 1 would go over square root of 2 over 2 and up square root of 2 over 2. So the coordinates for here is the square root of 2 over 2 and the square root of 2 over 2. Now, if I was up here, this is, I went over 0 and up 1. This one, I went the same. It's going to be this point right about here. And I went over negative square root of 2 over 2 because I went into the negative direction, and then still up square root of 2 over 2. So this is negative square root of 2 over 2, square root of 2 over 2. And then this point right here, I went over negative 1, and I didn't go up any. Going over to here, yet again, my 45-degree angle. Now I'm in the quadrant 3, so I went over negative square root of 2 over 2, but this time I'm going down square root of 2 over 2, so these coordinates are negative square root of 2 over 2, negative square root of 2 over 2. Yet again, not thinking any different numbers, it is all coming from that going the same distance, x and y, with that 45-degree angle, or the pi over 4 radians. This point is going to be 0, negative 1. And then this point, I am going to be going over square root of 2 over 2 in a positive direction, but this time down square root of 2 over 2. So unit circle, it's really just looking at those same triangles, just which quadrant I'm ending up with. So if I was drawing my triangles in here, I have this triangle here, this triangle here, this triangle here. They should line up. Yet again, not good at straight lines. Okay, we always go to the x-axis because that will help with all of the other angles that we're talking about. Standard position, we're talking origin for the vertex, initial side, positive x. Terminal side is just where it's going to end. It's going to go to a point that you have with it. And you go counterclockwise when you're talking about that. So looking with our unit circle concepts again, this gets really messy really quick. So I usually make separate unit circles depending on which angles I want to put on here. So we're going to make another circle. Well, another set of axes. It's not really a circle. I still call it the unit circle because we're still talking the distance. Those are uneven, but that's okay. All right, so we've got 0, 0 here. We've got a point here, which is going to be 1, 0. We've got a point here, which is 0, 1, our quadrantal angles. And this is negative 1, 0. And this is 0, negative 1. I put that in the wrong spot. Love it. I'm now worried that I just messed up my... Okay, good. 0, negative 1. Cool. And if I'm talking my angles, this is, I'm just going to do radians, pi 0 and 2 pi. This is pi. This is pi over 2. And this is 3 pi over 2. Now, thinking of our special right triangles that we did up here, we did the 45s on this one, breaking the circle into 8 parts, or the top of the circle into 4 parts. So that's how we get the pi over 4s. The other special right triangles are the 30, 60, 90s. And if we think about this, 180 degrees divided by 6 gets me 30. If I divide by 6 by if I so if I divide by 60 degrees, I would get 3 of them. If I divide by 30 degrees, I will get 6 of them. So we're going to break the top of the circle into 6 parts. They are going to be a little offset. Yeah, cool. The 45 would be right in the middle of it because it breaks the sections up. Yet again, drawing without rulers, without measuring, this is not going to be completely accurate. And my lines are definitely not straight. We pretend. Cool. We pretend I am an art major. No. So this would be, I've broken it into one. Ooh, that's really not good. I gotta fix these ones. I really should just use the line tool. Actually, I really should, but I don't want to. Okay. That's closer. All right, so this is going to break it into 1, 2, 3, 4, 5, 6. So this is going to be pi over 6. This will be 2 pi over 6, which is just pi over 3. This is 3 pi over 6, which becomes pi over 2. This is, so 1, 2, 3, 4. 4 pi over 6, which is 2 pi over 3. 5 pi over 6 doesn't reduce. This is 6 pi over 6. The 6's will cancel out and you get pi. This is 7 pi over 6, which doesn't reduce. This is 8 pi over 6, which is just 4 pi over 3. 9 pi over 6, which is just 3 pi over 2. 10 pi over 6, 10 pi over 6. 2 goes into both of those, so that's 5 pi over 3. And 11 pi over 6. And this gets me back to 12 pi over 6, which is just 2 pi. Now, with these, we are going to be drawing little triangles in it because we need the points. We need to know where they go. So the first one I'm going to do is going to be about here, where my radius is still 1. Radius is 1. This was my 30-degree angle. It broke it into the 6 parts. So if I'm looking at my little right triangle that I'm drawing here, the short side is going in the Y thing. It is a short triangle and not a tall triangle. If I was talking this one and draw my little right triangle here, this is a taller triangle, meaning my longer distance is going to be my up and down. My shorter distance is my across, which is my X and my Y. So thinking about the orientation of these triangles is going to help you get your points. And honestly and truly, I try to memorize as little as humanly possible. Ooh, that's not good. What's happening? I have something close to my drawing pad that's causing problems. All right. So when I'm thinking about this, remember I have my special right triangles. Those are always going to be in that. Those are the numbers that I have for my sides or my distances. I have the 1, 1/2, and square root of 3 over 2. I have to think of what is my short side. And in the first triangle, the short side is the up and down. So this coordinates is going to be, ooh, I want a different color. I wanted this color. Okay, so it's going to be, I went over the longer number, which is the square root of 3 over 2, and I went up 1/2. In this triangle, I went over less, so it is a taller triangle, so I went over 1/2, and I went up square root of 3 over 2. Okay, making the next right triangles, thinking approximately here. And as you look at your points, you're going to see that you've got your circle mapping out. I can kind of see it a little bit better in my 45s or my pi over 4 radians. This triangle is going to be a taller triangle if I can visualize it without drawing it. So that means that my X is going to be my smaller and I'm going in the negative direction, and my Y is going to be my taller. All right, over on this one, I went over further than I went up. So this is going to be my negative square root of 3 over 2 and my 1/2. And that is literally how I go around my unit circle, getting all of the quadrants in there. I'm not going to, right now in the summary, finish those, but that's how you're going to do this. Now, for degrees and radians, when we're talking those, I'm going to use this. Degrees to radians, we can use any comparison that we have on any of these coordinate grids or unit circles that we have. Math people, I mean, me personally, I tend to be as lazy as possible and want to use as easy a numbers as possible, meaning I don't want to deal with fractions if I don't have to. So yes, I could do 135 and 3 pi over 4. That is a good comparison because they end up at the same spot. I could do 90 and pi over 2. Yet again, I want to do with decent numbers, so I'm going to use that 180 and the pi. The ratios that you're going to be always comparing to, you can either do pi over 180, depending on if you want to get your answer to be in radians, or you can do 180 over pi, depending on what answer you're looking for and what you start with. So thinking of an example, if I have 200 degrees, and that is what I was given, I am going to need the degrees to cancel out. So I would be using, I want radians in the answer, so I want my pi on my top. So I'm going to multiply it by pi over 180. Now, whenever I'm dealing with fractions, it's easiest to deal with a fraction and another fraction. So 200 is the same thing as 201. If they didn't give you a fraction, make it a fraction by putting it over 1. Now, when I'm looking at this, my degrees cancel out. I can divide both of them by 10 and get the zeros to cancel out. And then I can divide 20 and 18. 2 goes into both of those, so this becomes 9 and this becomes 10. Multiply straight across. I find it always easiest when I'm multiplying fractions to reduce first, because I'm dealing with much smaller numbers. I do not like dealing with big numbers yet again. It's me being lazy. No, it's me just looking for the slightly easier ways to work with it. 10 pi over 9 would be my radians that are equal to 200 degrees. Now, say they give you radians and you want to go 2 degrees. So let's give you, well, yeah, so I'm going to give you 5 pi over 12 radians, 12. And I'm going to say we need this in degrees. So in this case, I want the degrees to be my answer. So I want to have the 180 over pi. Now keep in mind, if they can give you radians without the pi in it, it's still going to use the same radian. It's just going to mean that they've multiplied that pi, which is 3.1415 and keeps going, into your number. It's still there. It's just already multiplied in. So you would still leave the pi in your answer. It'll just be in the denominator. So in this case, oh, awesome. I definitely have a magnet somewhere that should not be there. All right, so in this case, my pi cancels out with my pi. I know 12 and 180 can be divided by 6. So this would be 2. Divide this by 6 and I'd have 30. And then I can't divide anything else out. If I had to do the 12 and the 180 by a couple different numbers, the purpose is to get it as small as you can. Now I get to multiply across. 5 times 5 times 30 is 150 over 2. I actually should have done more. Realized I didn't divide it enough. So 150 divided by 2 is 75 degrees. All right, so degrees radians, it's really just dealing with that conversion factor where you have it. Coterminal versus reference. Coterminal means they have the same ending point. So coterminal is going to be add or subtract. Whole circle. So if you're starting in degrees, you're going to add or subtract 360 degrees. If you're in radians, you're going to add or subtract 2 pi. And it's just going to be, you think of it as a spinner for a game. You could go positive or negative directions. And it's just, you're going to be going however many times around, but it's where it ends. Reference angles is always triangle to closest. And when I say triangle, I'm really making these little triangles like we did with our unit circle to get that angle. Triangle to closest x-axis. So however many times you go around the circle, doesn't really matter. You're always going to be either going to either the 180 or the 360 or the pi or the 2 pi is where you're looking at. If you're in quadrant 1, your reference angle is going to be the same as the angle that you already have. So quadrants are going to help you knowing which the values of positives and negatives in each of the quadrants is going to help you and working with that. So then we're going to talk trig ratios. So hopefully in some class you have heard of the SOHCAHTOA. Yet again, we are working with right triangles. We're going to have a generic right triangle, and I really should use my lot drawing tool, but I'm really not going to. Okay, not too bad. Right triangle, remember that we have the hypotenuse. My opposite, because I'm always going to be standing here. Okay, you could stand at the other thing, but it's just going to affect what your opposite and your adjacent is. We want to be in standard notation because we're going to be talking um, in the quadrant plane, and we stand at the origin when we can get everything into standard position. This will be my theta. It'll be whatever angle they have labeled. Um, you can rotate these, you can flip them into whichever quadrants, however, sides are going to be very similar. They could label the other angle, and you could be finding that these two angles are always going to be complementary, meaning they'll add up to 90 degrees because they have to make a triangle. Triangles add up to 180. Supplementary will make the 180 degrees, meaning that they're going to add up to 180, and that's what you're going to have when you have those reference angles. They're going to add up to either 180 or 360, or they're going to add up to pi or 2 pi, depending on if you're in the upper half or the lower half of the quadrants. So this is hypotenuse. This is my opposite. It's always going to be across. And this is my adjacent. Okay, and then what the SOHCAHTOA means is that you got sine. So this is sine, cosine, tangent, 1 over cosine equals the secant. 1 over sine equals the cosecant. And 1 over tangent equals the cotangent. Now, what these are is they are ratios. They are telling you what to do. They are telling you a comparison of sides. Because they are something that is telling you what to do and a comparison of what you're having. So it's a rule. They are functions, meaning I need to have something to reference into, meaning I need to have an input. Otherwise, they really don't tell me anything other than this is a formula I have, or this is a rule I have. So when we are doing this, and I know it's very tempting to get lazy and not write everything that you need, we are going to always have whatever angle we have. And in this case, it's mostly going to be thetas. A lot of times it's going to be some Greek letter. We could do alphas, we could do betas, but we're going to do thetas. So this means that sine of this angle, so when I'm standing here, it is going to be the opposite over the hypotenuse. Okay, when I'm doing the cosine, I need to know where I'm standing, and I'm standing at theta. And this is going to be the adjacent over the hypotenuse. And same with the tangent. I need an angle. If I do not write the angle, I do not actually say I'm doing anything of that makes sense. Opposite over adjacent. Okay, but we are, and then if I really want to do the other six, there's 6 trig functions. So if I want to do the reciprocals, this would be cosecant, and it is just the reciprocal of the sine. So this is hypotenuse over opposite. This is secant. And cotangent equals adjacent over opposite. All right, so if I'm looking across, I have a regular function, so sine, and I have a co-function, which is the cosecant. I have a cosine, I have a regular secant, so that I can remember which one goes with which with those. Now, because we're thinking of the coordinate planes and we're thinking of our little triangles, the adjacent to us, or where we're talking, that is going to be in x direction. The opposite is going to be a y coordinate, y direction. So these functions actually will change to, I'm going to do it in black. Okay, so the opposite is going to be my y. My hypotenuse is my radius. If my radius is 1, then I'm on the unit circle. And then the cosine is going to be the adjacent, which is the x, over the radius. The tangent's going to be the y over the x. So the height over the side next to you. Doing for the rest of them, this is going to be r over y. This is r over x. And this is x over y, which is going to make our Pythagorean theorem become, yet again, as I wrote at the top, x squared plus y squared equals r squared. Now, that means I can find any trig function or any trig ratio for any point that they give me, because x and y's are coordinates. So say I give you the point 8, -15, because I like bigger numbers. Not really, but we're going to look at this. This is my x. This is my y. So what I need to do to find any of this, I need to know what my x equals, what my y equals, what my r equals. If they don't give me my r, I need to find it. So to find my r, I know I have 8 squared plus -15 squared. I always use parentheses, especially with negative numbers, equals r squared. So 64 plus 15 squared. If you don't know it, 15 squared is 15 times 15, which is 10 plus 5 times 10 plus 5, which is 100 plus 50 plus 50 plus 25, which is 225. Yeah, I multiply weird. 225 equals, that's if you do not know your perfect squares up to 20. Up to 20 is usually useful. A lot of people stop at 12. However, the slightly bigger numbers do make your life a lot easier. However, you can always multiply numbers together if you cannot remember them. Yet again, no calculators. So this is 289 equals r squared. Remember, r has to be positive, so when we square root it, r equals 17. Hopefully you know your square roots or your perfect squares. Now, because I have 8 and 15, I could draw this picture, 8 and -15. 8 positive -15 is going to be somewhere around here. So this is my triangle. This is -15. This is 8. I'm in quadrant 4. So they could give you some information with telling you one of the values is negative. They could tell you what quadrant you are. They could even tell you one of the functions being positive or negative. You can always figure that out by drawing your little grid. If they didn't tell you which one it is, and then think of your possibilities. So now that I know my x is 8, My y is negative 15, and my r is 17. Remember, your radius is always going to be a positive number. Now I can tell you that my sine of the angle they're asking me for is going to be negative 15 over 17. My cosine is going to be my x, so 8 over 17. My tangent is going to be my negative 15 over 8. And then I can do the reciprocals, cosecant theta equals, and yes, I do realize that it gets tedious to write that theta. You have to do it. And notice when I did the cosecant, my negative one on the bottom, it really doesn't matter. The whole fraction is negative. I can have my negative on the top, negative on the bottom, or negative in front of it. It all just helps me when I'm thinking of what values that I have. So x's and y's. 8 over 15, and I'm just going to say the whole thing is negative. So they're going to change depending on where you are. Now, because of this, you can also figure out the opposites of it. We are going to be finding angles. Sometimes we're going to be finding, figuring out what the angle is, and they should be ideally unit circle things because we're not going to be using calculators, which means our angles are going to be on these unit circles. So we can talk pi over 6s, pi over 3s, pi over 4s, and all of those things. So if I tell you that my point is, and I give you the coordinates, you can give me all my trig functions. Yeah. So that's points on the unit circle. We're going to do another video because this is getting really long of going backwards. So if I give you the sides, can you give me the angle from that? And it's really just going with, yet again, making a right triangle, seeing what you have, and going from there. So hopefully this will help for summarizing week 1 if you're getting a little bit behind on the homework. It is okay. However, you do need to know all of this stuff. It is not going away. Even when we're doing other topics, you're going to still have some problems to do on this. It might be in the worksheets. It might be in WebAssign. We'll see. All right.